Can an operator in an infinite-dimensional space ever behave with the algebraic predictability of a finite-dimensional matrix? In finite-dimensional geometry, the rules are stable. According to the Heine-Borel property, any set that is closed and bounded is compact. This property ensures that a sequence of points within a bounded finite space cannot wander indefinitely. The points must eventually cluster around a limit. But in an infinite-dimensional space, like the sequence space L2, this requirement vanishes. Here, a sequence can be perfectly bounded but still escape accumulation. In L2, each basis vector maintains a constant distance of the square root of 2 from the others. Because the space is infinite, the sequence can simply occupy a new dimension at every step, never clustering. The compact linear operator was designed specifically to arrest this behavior and force these escaping sequences to cluster. By forcing infinite-dimensional spaces to obey the topological rules of finite ones, these operators provide the mathematical stability required for physics and engineering. Definition 8.1-1 states that a linear operator is compact if it maps every bounded subset into what is called a relatively compact set. This means the operator maps an infinite set of points into a region where they are mathematically forced to cluster. It compresses infinite chaos into a manageable form. Lemma 8.1-2a shows that because a compact operator maps the unit sphere to a bounded, compact set, the operator itself must be bounded and therefore continuous. However, continuity does not imply compactness. Consider the identity operator on an infinite-dimensional space. When the unit ball passes through the identity operator, it remains bounded, but it does not become compact. The sequence of basis vectors still fails to accumulate. While all compact operators are continuous, continuity alone does not guarantee the topological compression required for compactness. Theorem 8.1-3, the compactness criterion, shifts this definition from sets to sequences. Under this criterion, if you feed any bounded sequence into a compact operator, the output is guaranteed to have a convergent subsequence. The compact operator acts as a topological sieve, filtering out the infinite-dimensional points until a single, predictable, convergent signal is isolated. Theorem 8.1-4 applies this logic to any operator with a finite-dimensional range. Because the range is finite-dimensional, the Bolzano-Weierstrass theorem ensures that every bounded sequence in that range has a convergent subsequence. This means all finite-dimensional operators are inherently compact, serving as the baseline for understanding their infinite-dimensional counterparts. Theorem 8.15 establishes that the uniform operator limit of a sequence of compact operators is also a compact operator. To prove this, we take a bounded sequence X sub m and a sequence of compact operators T sub m. Using Cantor diagonalization, we can find a single subsequence that converges for the limit operator, T. First, we use the compactness of T1 to extract a convergent subsequence from the first row. We then apply T2 to that first subsequence, extracting an even more refined subsequence. This process of extraction repeats for every operator in the sequence. Selecting the diagonal sequence, y sub m equal to x sub mm, isolates a single path that is a valid subsequence for every operator in the list simultaneously. Because T sub n converges uniformly to T, we can show that the image of this diagonal sequence is a Cauchy sequence. In a complete Banach space, every Cauchy sequence converges. Therefore, T maps our sequence to a convergent limit, proving T is compact. This theorem allows us to verify the compactness of an infinite operator by approximating it with a series of finite matrices. In example 8.1-6, we define an operator T on the sequence space L2 that divides each term by its index, j. We can approximate this by creating operators, T sub n, which truncate the vector after the nth term, filling the rest with zeros. Since each T sub n has a finite-dimensional range, each one is compact. The distance between our original operator T and the truncated T sub n is bounded by 1 over n plus 1. As n grows, this distance shrinks to 0, proving uniform operator convergence. By Theorem 8.1-5, we have proven that the original infinite operator T is compact by treating it as a series of finite truncations. Compact operators also upgrade the quality of convergence. Theorem 8.1-7 states that if a sequence converges weakly in its domain, a compact operator forces its image to converge strongly. If we assume a sequence converges weakly to X, but its image does not converge strongly to Tx, we reach a contradiction. A weakly convergent sequence is bounded. Since T is compact, this bounded sequence must have a subsequence that converges strongly to some limit, y. Because every strong limit is also a weak limit, y must be equal to Tx. The assumption that the image does not converge strongly is logically impossible. This means compact operators act as amplifiers, taking diffuse, weak signals and forcing them into strong, measurable outputs. These structural constraints provide compact operators with further predictable properties, such as those involving totally bounded sets. Theorem 8.2-3 shows that the range of a compact operator is always separable, meaning it can be completely covered by a countable dense subset. Theorem 8.2-5 adds that if an operator is compact, its adjoint operator is compact as well. These proofs confirm that compact operators consistently map infinite-dimensional complexity into structures that mirror the simplicity of finite dimensions. This is what makes them indispensable for solving Fredholm integral equations, where continuous functions must be resolved through linear algebra. It explains why quantum mechanical systems, despite existing in infinite-dimensional Hilbert spaces, exhibit discrete, observable energy levels. Compact linear operators provide the mathematical framework that brings infinite-dimensional spaces under the same algebraic control as finite matrices. They are the mechanism that makes the abstract physics of infinite systems both predictable and calculable.